Good afternoon and welcome to quantum computing. So last week we discussed selected algorithms and in particular looked into Crovers and Shors. And every year they will be discussed in greater detail in some of the seminar presentations. So that should be some other hint for the seminar. And we've already looked into the theoretical limits of quantum computers. So we have two chapters left. And at the end of today's lecture, I will also say more about the seminar presentations. Last week, we were also super happy to have Rolf Hoyer as a guest lecturer. So Rolf ran CERN. He was the director general there. And I think his lecture yesterday provided you with some additional insights on physics, not on quantum computing, but on particle physics. And only some of you have done the course evaluation so far, so I would be very happy if more of you do the course evaluation. And I've just sent the reminder also via iLearn. And today we will look at the last challenge. So we've seen plenty of challenges, and the challenges we looked at what are the limits of quantum computers. We've seen the challenge of coming up with concrete algorithms. Now the next challenge is we need actual quantum computers to run all of this, and we need to know how to program them. This is what we will discuss today, and we will look at, first of all, concrete quantum computers. What are some goals and challenges of such machines? We will discuss decoherence again. We've seen decoherence before, but we'll see it now from a more practical perspective. We will see different architectures of quantum computers. And in one approach is quantum annealing, which is related, or it's just some concrete variation of adiabatic quantum computing. And at the end of that chapter, there will also be a programming exercise. So you will be able to run code on a real quantum computer. So quantum computing, from its theory, goes back to the 1980s when the first proposals about quantum computers were made. But those were purely theoretical, and then we saw that in the 80s and 90s, certain algorithms followed, but there were no quantum computers that could actually run all of this. Now we have limited quantum computers, at least something, but we have machines that are available nowadays, and that's something that was not the case in the 1980s. So when we have a quantum computer, we not just want to have it, but we actually want to have a computational advantage, meaning we want to solve real problems and run them faster than a classical computer would do, and not just by a certain factor faster, but actually faster in terms of a better complexity class. And in order to do this for real world problems, we need a lot of qubits. And there's sometimes this term quantum supremacy. It's a term that some people don't really like, but quantum supremacy means eventually quantum advantage, but we rather speak here about quantum advantage. And we want these quantum computers to allow us to run quantum algorithms reliably. We will see some challenges as well, but it's one of the goals that at least when we have quantum computers with a lot of qubits, we want to run all of this reliably. And eventually we want to outperform classical computers in specific tasks. We have already seen when we looked at the theoretical limits of quantum computers that quantum computers will not just magically outperform every computer in every task. Rather, quantum computing addresses a certain niche of problems that we have discussed in this course. Now, there are challenges. First of all, we need to be able to build lots of qubits in a quantum computer. And you will see there are different architectures with a few dozens of qubits to a few thousands of qubits, but those are all totally different architectures. But it's not like we have suddenly millions of qubits available. today. And then we will have noise and decoherence. So decoherence means the quantum system starts interacting with its outside world. We will see more about this today as well. So decoherence is an issue and it contributes to the uncertainty when we run a quantum algorithm. So we've seen uncertainty already in the measurement, but then also typically the more gates we use or the longer the quantum program runs, the more decoherence we suffer from. And decoherence means our quantum system loses its purity. So we again add uncertainty. And if we get a lot of decoherence, then eventually we just get lots of garbage. So how can we address decoherence? There are lots of different proposals. There are some proposals of quantum computers that would not suffer at all from decoherence, but that is largely theoretical so far. So the quantum computers we have available today, they suffer from decoherence, so the coherence gets lost in the quantum system. And one proposal is that we do error correction, so that we add qubits for fault tolerance, so that we not just recognize errors, but we correct them. But the challenge is again, when you add more qubits, you need more qubits for the error correction, and adding those extra qubits will again further increase your decoherence. So just adding qubits does not necessarily solve the problem. We'll later see some plots in order to understand that relationship in greater detail. And one challenge is obviously that we scale to a lot of qubits, maybe some architectures like the IBM one to thousands, or the D-Wave one to millions, or the IBM approach even to millions of qubits. And we need way more qubits so we can run these quantum algorithms actually on quantum computers for a sufficient input size. So those are massive challenges. And when you talk to different companies and different people, obviously, you hear all sorts of answers from them, how they would address this. I think the IBM CEO said to him, all of this was just an engineering problem, not just a science problem. I think it's really a science problem, by the way, and not just an engineering problem. And eventually, for quantum computers to become more mainstream or be adopted by a lot of companies, we need way more qubits and address decoherence in some way. And that's not just an engineering problem, it's actually a science problem, and there's lots of uncertainty how quickly we can scale up, whether that's actually possible in the foreseeable future. And you're now somewhere in the midst or in the end of your studies, and you have 40 or maybe 50 years ahead in your career. I'm sure there will be lots of progress with this, but how quickly, we don't know. And this course is also meant to prepare you for this quantum future in the coming years and decades. And for these goals, there are so-called de Vincenzo's criteria, which were proposed in 1996. And these are some criteria for quantum computers. So we need a scalable physical system, means scalable, more qubits. We want long decoherence times, so decoherence takes a long time to actually kick in. We also want a universal set of quantum gates. We've seen quantum gates already a lot in this course, but we also need an ability to initialize the state of qubits easily, because when we start running the quantum program, we need to access the quantum computer from outside, from the classic world. And there must be some easy way how we can actually initialize these qubits to 0 and 1. And after that, we've seen in our generic setup of quantum algorithms, we need some, typically a harder MOT gate or something to create a superposition, at least on some of the qubits. But we need to be able to easily initialize the state of qubits. And we need some measurement functions, so we need to be able to collapse the qubits into classic values, which we then access from outside as well. So these criteria were already established almost 30 years ago. And in order to build a quantum computer that satisfies these criteria, there are lots of challenges. Now, decoherence is a big challenge, and decoherence means that our quantum system starts interacting with the outside world, and then we lose information or we lose the purity of that system. Now, what are the sources of this noise or decoherence? For example, cosmic rays, crosstalk between qubits, material imperfection, thermal effects, and so forth. And we've seen one architecture already when we started with this course in the very beginning of the term. We saw the D wave approach, and we saw that this one is cooled down to just like I think a dozen or 2 dozen of millikelvin, as you remember. So thermal effects can also kick in if I don't achieve the temperature, or if I am slightly above the desired temperature. This would also create some noise. So all of those are challenges. Now, we actually want to keep the coherence longer, so we want it to take longer until decoherence kicks in. So we want to keep our qubits there, and we want the qubits to keep their pure state long, but we also want our gate operations to be fast, so that running an individual gate is actually super fast because we need multiple gates in our quantum circuit for our algorithm. And typically, the longer these operations run, the more decoherence will come in. So we want these gate operations to be super fast. And we want all of this to be scalable so that we can actually have many, many qubits that somehow can interact with each other, and we can control this interaction through our gates. Now, you could wonder, is there some way to perfectly isolate the quantum system from the outside world? Well, not really. And even if we had that, so if we could totally eliminate decoherence by totally shielding off our quantum system from the outside world, then we wouldn't be able to interact anymore with the circuit. And we still want to somehow control that circuit. We want to feed in something. We want to read out something. Maybe have some control operations from outside. And if we were to totally isolate the system from the outside world, then that wouldn't be possible anymore. So we want actually be able to control these operations in some easy way, but we also don't want to totally shield it off, because then we are unable to access it any longer. So this is a compromise you would need to make when you build such quantum computers. Now, I've mentioned error correction. We can add more qubits for error correction, and there are different architectures for this and all sorts of roadmaps of how this could evolve with various vendors. Sounds cool. We just add more qubits for error correction, but the reality is when you add more qubits, this leads to additional decoherence. And then we add again more qubits for that additional decoherence and more, and then we get even more decoherence. And that's certainly a problem nowadays. And that's why there is a different term that is actually useful. It's the quantum volume. And the quantum volume means it's a certain number of qubits or a certain number of units that you can effectively use. Because just adding qubits doesn't mean you can use all of this because of decoherence, and you add more qubits, and then you have maybe error correction, but again, you have more decoherence. So we want to have a certain number of qubits we can effectively use. And that's what the quantum volume refers to. And there's a figure from IBM of how this quantum volume has evolved over the recent years. I didn't find a newer plot that shows this very nicely, but the idea is simply there are architectures, and over time, they not only had more qubits, but actually qubits that could be used effectively because of error correction, of decoherence, and so forth. Because if you just add more qubits and all these extra qubits are used for your error correction, this would not lead to anything. So rather, we want to add more qubits and at least some of them will be effectively usable. That's the idea of the term quantum volume. There was some very interesting news just earlier this year of how Grover's algorithm could be implemented in a concrete quantum computer for which you actually would not need error correction and you would still get a very high accuracy. Most of that is obviously from a simulation point of view because we don't have these large quantum computers yet. But there was a very interesting article by Silicon Quantum Computing. Maybe something you wish to read to further explore this because they found a more efficient way also to implement Grover's algorithm with less gates. That's something we talked about also last week when we looked into algorithms. I mentioned another paper in that you need less gates than people had actually believed before to implement Grover's algorithm. And the consequence is also if you have less gates, this would lead to less decoherence because you just have less gates in your circuit. The whole circuit will just run, or the whole algorithm will just run faster. And that means there's less time for decoherence. But the reality is you still have decoherence. And then Grover's, so this is the black box search algorithm, just to remind you, would return you some answer, and that answer may be right, may be wrong, and that's why you still need to test the answer, apply it to the black box, and see whether you actually get the desired output. And the answer you get may not be correct because of decoherence, but also because of uncertainty from the measurements. And in worst case, you may just have to run it again and maybe a few times until you get the right answer. But that's not an issue because the Grover algorithm already provides you with a squared speedup. And now imagine your input size is 1,000,000 and you have a squared speedup, so O of square root of n. Then even if you run that algorithm a few times until you have the right answer, this doesn't make much of a difference because you already get that squared speedup. And it's even more significant if you have something that is better than a squared speedup, like an exponential speedup, for example. So even if you need to run the same program a few times, it doesn't hurt that much because typically you would get an answer, at least what is believed today, you would get the correct answer quite quickly. You just have such a massive speed up when running that algorithm. But this website here provides you with a few more details, so feel free to read this in case you're curious about the 98.9% claim. And it turns out there's a huge number of quantum vendors. So this figure here is also a few years old, but it's the most recent one I found that shows such a very nice ecosystem overview. So what it shows is we need quantum processing units, so QPUs or quantum processors. And we've already talked about IBM. We will see some of their work later. We've seen D-Wave, and there are many others. So, and this course is not here to promote IBM or D-Wave, it's just an example. But since you're all now thinking a lot about your seminar presentation, every year some students also present some of the other vendors and what they offer, like what kind of architecture they have picked, how to program it. So this could be maybe something for your seminar presentation as well. And the ones I had highlighted here are the superconducting QPUs, and there are lots of other approaches like ion traps, neutral atoms, photonics, silicon, or others. So there are lots of different ways how a quantum computer could be implemented exactly from a physical point of view. And this could be interesting for some of your seminar presentations. What you also need is when, for most of these architectures, you need to cool them down to absolute or close to absolute zero. So there are also cryogenic vendors that actually build that kind of cooling systems. There are other approaches like using lasers and so forth. So there are lots of different architectures how this could be built. Then there are software vendors and they all eventually aim that we can make quantum computing more abstract. So we don't need to think in terms of all these very low level operations that we've seen so far, but you have some more high level description. This is where the software part comes into play, and eventually there would be concrete applications like in finance and machine learning and so forth. Some of these QPUs are available through clouds, which is also the case nowadays for IBM and D-Wave. So this figure here is not anywhere complete. It just provides us with an overview. And eventually there are concrete end users exploring this. But for example, even if you see the BMW logo here, they may be an early adopter here in this figure, but it doesn't mean that they have hundreds of people working on this. So when I talked to someone from BMW, I think 3 years ago, they told me they had exactly like one person looking part-time into quantum computing. Nowadays, it's maybe a little bit more, but it doesn't mean that they are anywhere in terms of the number of people and investments near to AI or whatever. But they're exploring early. And you can see, for example, BMWs, they probably have lots of combinatorial problems from logistics, from car manufacturing, but you also see in life sciences like AstraZeneca, Boehringer Ingelheim, and others. So they are interested also in combinatorial problems and personalizing medicine and this kind of stuff. And this is where quantum computers can provide a speed up, but you also see there are some finance applications of quantum computers and some companies looking into this. And that's why I like this figure here that provides an overview. NVIDIA is largely now or still a GPU company, but they are also doing some early works now about quantum computing, but they're not building their own quantum computers as far as I understood, but rather they think about how AI and can be used for with quantum computers, and they provide some software and some testing environment. But I'm not aware that they are building, at least to a large scale, their own quantum computers yet, because they're still focusing on GPUs, and there's probably a big future for GPUs still. Yet they're already thinking a bit beyond. And I was at a large NVIDIA event in Paris in spring where they presented some of this. But so far, it's largely simulators or some combination of AI and quantum computers, but they are not a quantum computing or a quantum computer vendor yet. Let's see what the future would be. And maybe some of these topics in here could inspire you also for your seminar presentation. And I've mentioned there are lots of different physical realizations. You could have photonic qubits, diamond qubits, semiconductor approaches, superconducting circuits, ion traps, cold neutral atoms, or so-called nuclear magnetic resonance quantum computing. Maybe some of these topics are interesting to you to explore further and tell us in the seminar presentations how they work exactly. What I find very interesting is just as one example, IBM as a vendor. And I had just updated these slides, as you see, like a week ago, like 10 days ago. And after today's lecture, I will also upload the latest slide deck because IBM has this roadmap here, and this roadmap has made some progress since I created the slides during the summer break. And what you see in here is they have their past roadmap, so up to 24, and everything they had thought about, they claim they have completed. The reality is some stuff didn't work out as expected and they have removed it from their roadmap. So it's not like everything they wanted to achieve, they actually achieved, but they only probably leave the stuff in here they had achieved. So it's interesting to look into some deltas. And what you see here in 24, there is an architecture called Heron. It's 133 qubits. And now in 25, they switched to a different architecture with around 120 qubits. So you wonder why has the number of qubits decreased? Because it's not just the qubits, but also the number of gates you could use in here. So they are somewhere at a few thousand gates that could be used in a circuit at the most. And with this new Nighthawk architecture, the number of qubits has dropped a little bit, but they have more potential for additional gates. And in the future, they would also increase the number of qubits in a couple of years. But they consider now, or for them, it seems to be more important at present time to add more gates or gates that could be used rather than increasing the number of qubits. But in like 8 years from now or something, or well, let's say in 4 years from now, they want to make it to up to 100 million gates and 200 qubits. And somewhere in the future, beyond 2033, they think about 2000 qubits and even 1 billion gates potentially. I think all of this is highly speculative, and something I've noticed is they have very interesting stuff in here, like error correction and so forth. Um, and these roadmaps, they look really cool, but when you talk to the people who come up with these roadmaps, if you talk to them in private, they are actually far less sure if all of this would materialize anytime soon. So I'm not mentioning any names, but the roadmap is the one thing. Whether all of this could be achieved is a different topic. And what they also mention in here is software packages and so forth, algorithms. So they also want to make some more progress here on the software side. So the lower part here is, or at least the dark part is the hardware side. There's some software side plus here for algorithms and so forth. So, and you see there are lots of challenges. And if you look back maybe from say 5 years ago, there were maybe some other things in this roadmap here that they didn't achieve, and it's now been deleted or been renamed. So they're very ambitious, and I think IBM is certainly one of the leaders now in quantum computing. And from today on, feel free to check their roadmap from time to time and see how it's evolving. They have already achieved something they wanted to achieve next year, so that looks very positive. But they keep updating this roadmap all the time. But you see, so by the end of the decade, they hope to be at like 200 qubits. Currently, they're at 120, 133, but the goal is reducing errors, but also increasing the number of gates. Um, and this is the IBM roadmap. We will later come back to IBM when it comes to the coding exercise. There is another vendor that I find personally very interesting. It's called SpinQ. It's a vendor from China, and they have built quantum computers based on nuclear magnetic resonance, something that actually runs at room temperature, by the way. So you hear the IBM approach, this is all cryogenics, you need to cool down. But here, the NMR, so the nuclear magnetic resonance quantum computing, runs on room temperature, and spin Q, they have they're not building large scale quantum computers, but rather quantum computers for educational purposes. So you can carry such a quantum computer, you can carry it to a school or a classroom or to a company. And some of their machines, they have maybe 2 or 3 qubits, or now maybe a few more qubits. So it's more like an educational setup, but it's a quantum computer you can carry around. So when I taught this course 2 or 3 years ago, I still taught it together with Horst Kuhnhardt, who just retired in the summer. We were actually very interested in buying one of those with 3 qubits, which was, I think, maybe like 70 or 80,000 US dollars. And we wanted to have one of those for this class and to take it to the classroom and take it maybe to companies. And um, inspire them early about quantum computers, but our university president at that time, he somehow did not want to fund this. And we could have been the first university in Germany having such a device. But we unfortunately didn't get that priority from the president at that time. So we stopped this. Yet, SpinQ, they keep writing me every few weeks if I still want to buy one of their computers, even if I'm not interested or not planning to do so anymore. I still receive a lot of spam from them, very aggressively trying to sell one of these machines. But I also don't keep begging our university for years for this funding because I just look at other opportunities. Uh, Now we've seen different physical realizations, and with that, we can also look at one approach in a little bit greater detail, and that's quantum annealing. That's the approach what D-Wave is doing, and we've seen these D-Wave machines at the very beginning of this course for a motivation, and they use an approach that is more tailored to certain problems. It's not universal quantum computing, and that approach is called quantum annealing. So what they do is they solve optimization problems by doing a so-called energy minimization. And there are lots of algorithms in classic computing for energy minimization, concretely annealing algorithms, which are inspired from physics or from manufacturing, where you use thermal fluctuations to escape local minima. Some of that stuff is also used in machine learning. I don't know if you ever heard about simulated annealing or annealing in classical computing. If you have ever heard about such annealing algorithms, maybe send me a thumbs up or thumbs down, and I'll just wait for your answers. So, at least one person has heard about this. And yeah, what you do is use thermal fluctuations to escape a local minima. And there's also a quantum inspired version, and with which we call quantum annealing. And we use quantum tunneling to escape local minima. And so we do energy minimization, and we want to get to the global minimum. And from a quantum computing perspective, this is especially suited for combinatorial optimization problems. So where we want to minimize a cost function, or we solve so-called icing model problems. I'll provide a link to more information about this later. And what the idea behind quantum annealing is that we have a system. It starts in an easily prepared ground state, and it evolves or anneals towards a so-called Hamiltonian HP, which represents the optimization problem. And the hope of quantum tunneling here is that it helps us to escape local minima better than using classical thermal annealing or simulated annealing. So we use quantum tunneling to escape these local minima better. And one way we can imagine this is the following. And I've taken here some figures from D-Wave directly. I'll get back to D-Wave in a moment. And it's not any marketing here for D-Wave, but rather they have some good figures to visualize this. And the idea behind this annealing process is this energy diagram. And what we want to do is we want to raise the energy barrier for a single qubit. And then we get to this 50-50 probability of ending in a classical state of 0 or 1. And now, when we have annealed to this, we could also obviously apply various other operations by using an external magnetic field, and we apply this to the single qubit, and eventually, so this external magnetic field, that would be some operations on this qubit or on this qubit, and it would eventually result in a higher probability of ending in a classical state of 1. D-Wave is one vendor for this approach, and every year there are one or two groups in the seminar presentations that tell us more details about how the D-Wave architecture works internally. So what you probably remember from D-Wave when we started with this course 2 months ago was that there are thousands of qubits in modern D-Wave architectures, but it's very important that there are some constraints, and it's a totally different approach than the IBM one, which has maybe 120 or 130 qubits. But with this quantum annealing, this has some very interesting applications in logistics, in financial optimization, in material science, and D-Wave has been building such machines now for more than 10 years. And there are also some of them in Germany, for example. If you look at the research center in Jülich, they have invested early in D-Wave machines and started to do experiments for their research problems there. But it's very important to highlight that the D-Wave approach is not general purpose quantum computing, because most what we explored so far in this course was general purpose quantum computing with the gates and so forth. But rather, this D-Wave approach is a very problem-specific machine for example, applications in logistics, financial optimization, material science, and so forth. And here we also have a comparison of different D-Wave architectures. So the one we saw when we started with this course 2 months ago is the D-Wave 2000Q, which has more than 2000 qubits. But what is this chimera topology? These 2000 qubits, they are not all interconnected. That's very important. Only a few of them are connected. And then you have like this group of qubits that is connected, and you would connect this to some other group as well. And if you have a very big computation to do, you would need to have a lot of these groups, and they would need to be interacting. And this would also use up a lot of these qubits quite quickly, simply for connecting these groups of qubits. And over the years, D-Wave has offered new machines like the Advantage QPU or the latest Advantage 2 QPU, which appeared as a prototype last year. And obviously, they always claim that this is like 10 times faster than the previous one or 20 times faster than the one before. What you see is the number of qubits, first of all, went up and then went down in the latest architecture. But what is also important is the connectivity, how you can connect these qubits. And they use also a different topology now, as you can see here. So you can have more qubits connected with each other in each group. And for this, you need more of these couplers. And eventually, they still claim that this is 20% faster than the previous one. And the one before, they claimed is 10 times faster than the one before. Obviously, a lot of that is marketing. You know, the same. I don't know. I bought a new iPhone recently, and they claim, you can use the battery to watch a movie for 30 or 40 hours. It barely works this way. It's typically made up for some example. Nonetheless, there is progress here, especially when it comes to this connectivity, which would then allow us to solve certain problems much faster because we just have less of these groups that need to uh, interact with each other. And you can also access machines from D-Wave anytime. I had shown you this in the very first lecture where I've shown you there's a web portal and you can either simulate or you can run this on a real D-Wave computer and you get some time for free. Otherwise, you pay extra to get some extra computing time. And D-Wave offers this. Feel free to test this. But I have to tell you, the D-Wave approach is overall quite intensively debated in the community. Some people really believe in it. Others, they are very, very negative about D-Wave. So there is some criticism towards D-Wave. Some claim that the D-Wave approach would not lead to any speed up eventually, that classical algorithms would often perform similarly or better on similar problems, and that the D-Wave approach would introduce lots of errors, decoherence, and so forth. And if you just use the classic computer, all of this would not happen. And there is this limited qubit connectivity I've mentioned, which leads to large overheads when you have a lot of these groups that need to interact with each other. And that would effectively reduce the problem size. I had mentioned this before already. And some people, they claim that the D-Wave performance claims are sometimes overhyped or very problem specific. And there's this doubt whether the D-Wave approach would actually lead to any quantum advantage. I think that the problem specific one is something that not only D-Wave uses for marketing, it's others. You've seen this with Google, that they claim they could suddenly solve something that would otherwise take hundreds of thousands of years or something like this. They too use a problem that is maybe inherently made for their architecture, which a quantum computer could then solve much, much faster. And the question is, does this apply to lots of other problems as well? So I think the criticism that D-Wave faces here is criticism that not only D-Wave should face, but other vendors too, that obviously some of these claims are problem specific. But overall, D-Wave has found quite a few customers that are experimenting with this architecture or with that approach. And it's certainly the first vendor that built something that could actually be used. So I'm personally not that negative about quantum annealers, I have to say. It's maybe something that is only here for transition. Maybe in 20 years, no one cares about quantum annealers anymore. And we use much larger universal quantum computers. Could be happening. I don't know. But at least today, at present time, these quantum annealers are probably the approach that runs the best and leads to actually concrete outcomes. And as I've said, D-Wave has found quite a few customers and they keep investing, so it's probably not running that bad as some people claim. But the D-Wave thing is contested. I think all of this D-Wave stuff goes back to some paper that was published maybe 20 years ago or something. And those who wrote the paper are not the people behind D-Wave. And those who wrote the paper, they claim that D-Wave had not fully understood their paper or whatever. So I just want to tell you that this is controversial. Um, and so you can do your own readings and come to your own conclusions about the D-Wave approach. And there is a question here. The question is if it's correct to say that adding qubits to counter decoherence is the same as adding some parity bits in classical computing. It's not exactly the same, but it's related. So in classic computing with error correcting codes, you add these parity bits. Yes. And so you add more qubits for the error correction, but adding these extra qubits for error correction again cause more errors or lead to extra decoherence. And so the parity bits in error correcting codes in classical computing, they don't add extra errors or uncertainty. So both, I think, are related, but the consequence is different. So I think, or I hope this answer has helped for the question we got here in the chat. Now, if you want to learn more about D-Wave, there are also lots of videos on the internet that explain how this quantum annealing approach works. Obviously, it's some sort of marketing for D-Wave, but I think you should come to your own conclusions about this vendor. I remember last year I was in Switzerland at an event. So the University of St. Gallen, they have a foundation for one of their degree programs, something like law and economics. And every year they invite some speakers from all over the world for a discussion. And there's some retreat in the mountains. And last year, the topic at that retreat was quantum computing, and I was also there. So very nice setting. I think it was last year in September or October in the mountains in Switzerland in some luxury resort. And so this foundation of the University of St. Gallen seems to have a lot of money, by the way. And we had discussions there with students about quantum computing. Most of these students were from law and economics, so they did not have this in detailed knowledge like you have now in technology, but they were just very curious about all of this. And they brought me in as a speaker, and they also brought in the leader of IBM quantum computing, Heike Riehl. She's German, but leads quantum computing of all IBM. So we had a very good discussion there in the mountains with the students for a couple of days. And they brought in some other famous speakers as well. But when I mentioned D-Wave, I felt from the IBM leader was a lot of resistance about the D-Wave one. So others love it, others are very much against it. So I just want to tell you that the whole D-Wave approach is controversial. But in the next chapter, I will have another reference to the D-Wave one and how you could actually take advantage of this. So there's this video here. Now, when it comes to quantum annealers, you oftentimes hear about so-called adiabatic quantum computing. Now, what is adiabatic quantum computing? Some people, they mix up adiabatic quantum computing and quantum annealers and treat them as synonyms. Um, and that looks tempting, but in fact, these are two different things, yet they are related. So adiabatic quantum computing is something more generic. It's actually the theoretical framework that underlies quantum annealing. And the way you can imagine this is you have a system that evolves slowly, and when it evolves slowly and it remains in its ground state throughout the evolution, then we speak about adiabatic, or then we're in adiabatic quantum computing, or that's the adiabatic theorem. And we also have this final Hamiltonian we need to get to, which encodes the solution, and we measure the final state, and when that gives us the optimal answer. So that's the idea of adiabatic quantum computing. And we can also describe adiabatic quantum computing. So we have this initial Hamiltonian or matrix, which is some easy ground state, and we have the so H0 and we have the problem Hamiltonian, HP, which encodes the optimization problem. And then we can define a time-dependent evolution, and we say h of t is s of t times our problem Hamiltonian, where s of 0 is 0, and s of large t, so at the end of the evolution, it's 1. So initially, this factor here is 0. So initially, h of t is just h of 0 because we have 1 minus s of t, but s of t is 0 where t is 0. And then as t progresses, we slowly evolve from h0 to hp. And if that evolution is slow or adiabatic, then the system stays in a ground state. And that's a mathematical description of adiabatic quantum computing, which is actually the basis of our quantum annealing. So there's a relationship between these two. So the relationship between quantum annealing and adiabatic quantum computing. So quantum annealing is, so for example, the D-wave approach is eventually a practical implementation or some special case of adiabatic quantum computing that you would typically use for optimization. Adiabatic quantum computing, at least in theory, could perform universal quantum computing if it's implemented with some sufficient control. But quantum annealing, so the D-wave approach, that one is not universal quantum computing, but rather used for certain optimization problems. And the quantum annealing approach, like the one that D-wave focuses on, is based on energy minimization than rather general quantum systems. So adiabatic quantum computing is something more generic, and quantum annealing is eventually a special case, and the D-wave stuff is based on quantum annealing. Now, for the IBM architecture, we also have a coursework for you in this course, and you are most welcome to do this either later today or in the coming weeks. So there is a Jupyter notebook in our Nextcloud directory, and you can open it and you can first simulate some quantum circuits. So there's a very simple quantum and circuit in here, and you can simulate it. And in fact, you run it 1024 times, and what you would get is, so it's 3 qubits. And when you measure, you would either get a 0, 1, 0 or a 1, 1, 1. And you see they are actually quite close to each other because there is, in fact, a superposition or an equal superposition. So, but when you run this, typically you don't get once 512 and 512, but rather two numbers that are quite close to each other. I have skipped the code where this quantum circuit is built, but you can see all of this in a Jupyter notebook, and you can simulate it. You can run it multiple times. You will get a different distribution, and you can also visualize this circuit. You remember there is the Harder-Matt gate, the C NOT gate, so the controlled NOT gate, a NOT gate, and we have the measurements. So you know all of these basic operations. You can think about what this circuit would look like and or what this circuit actually does. We've looked into all of these operations together, and what you get eventually is it's an equal superposition. And when you run this a second time, you would get somewhat slightly different numbers, most likely. Here, I have to give credit to Thomas Müller. So when Horst Kuhnhardt and I started teaching this course for the first time, which was in the winter term 2021-22, when we taught it for the first time, there was no coding exercise. And then one student, Thomas Müller, he actually created this Jupyter notebook and presented us this as his seminar presentation, and we just liked it so much. So we asked him whether we could make this Jupyter notebook available for everyone in this course, and he agreed to that. So you can, and this Jupyter Notebook uses Qiskit, which is this library. I think I mentioned it probably 2 or 3 weeks ago. It's an IBM library for quantum computing. You can simulate this circuit on your computer, or you can in fact run that circuit on a real quantum computer, which is the second part of the Jupyter Notebook. And what you need is an API token. So you need to create with the IBM Quantum Computing your own account, which is free of charge, and you get some tokens, or you get some free credit that you could use and run computations on a real quantum computer. And what you find in your account is an API token. So you would put your API token in here in the code, which I have not put my token in. Otherwise, you all get to use my token, and probably my account runs out of credit very quickly or gets closed. But you can do this free of charge, and you could run your own quantum circuit on a real quantum computer, and you could compare the output to the simulation. So and it's a very free coursework. You could build a more sophisticated circuit, whatever, and run it on a real quantum computer. So this is probably your opportunity to use a real quantum computer for the first time. And when I started this course, I had also shown you the D-Wave cloud. Same game. You can create your free account there. You could either simulate something on this quantum annealer, or you simulate, or you run it on a real quantum annealer, and that's a different approach you can take to run something on a quantum computer. So if you have never used a quantum computer, you can do this now as part of this coursework. Has any one of you already run or looked into this Jupyter Notebook? If so, maybe just send me a thumbs up or thumbs down, because it's in the Nextcloud directory for a long time. So none of you has tested it yet. Feel free to do this later today. And we now have one chapter left, which is a very small chapter, by the way, applications. So we can use, or if you're curious about applications of quantum computers, be it related to encryption, related to all sorts of other problems, obviously you can look into the course book. Even though this book is something like 17 years old, it proposed lots of applications, lots of algorithms, lots of theory. The only thing that has evolved in the meantime is now we actually have quantum computers available where we could run some of that. That was not available at the time the book was written, but the theory and the algorithms, obviously, they're the same. If you are curious about more applications of quantum computing, you can also read this book, Quantum Computing Since Democritus, which I've mentioned a few times in this course, which would provide you with the big picture of computing, quantum computing, theoretical limits of computing, and so forth. So the book is a tough read, but it will certainly provide you with a big picture of computing. And then, obviously, since many of you study AI, many of you could be interested in this intersection between between quantum computing and machine learning, which is quantum machine learning. And I think there are quite some interesting opportunities when it comes to quantum machine learning, because we could use quantum computers to train certain models much faster. That's one opportunity. Or we could also generalize much better from less data, because we could create lots of superpositions and from there generalize much better. So these are some opportunities when it comes to quantum machine learning. So train the models much faster or generalize better because we have limited data. Um, if you're curious about quantum machine learning, there are some good books. So there's one book, it's called Machine Learning with Quantum Computers, published by Maria Schult and Francesco Petruccione. They describe various quantum machine learning algorithms in this book, and it's the second edition now. And there's a very, very interesting course on EDX that I already took like, I don't know, 7 years ago or something. And it's called Quantum Machine Learning on EDX. And this course is really cool and can provide you with various insights into how to use machine learning and quantum computers. The author of this course, I think his name was Peter Wittek or so, he also wrote a book about quantum machine learning and largely used the D-Wave hardware for that. So if you want to learn more about quantum annealing and D-Wave, that course could be interesting. The only issue is the author of the course and of the book, Peter Videk, he died a few years ago. He was actually still young, but he got killed by an avalanche when he went hiking or skiing or whatever. So that was in fact a very big loss for the quantum machine learning community. Every year, students talk about these applications in their seminar presentations, be it quantum machine learning, be it quantum cryptography or information theory problems around quantum computing. And as you've noticed, we have now finished the lecture part of the course. I would be very happy if more of you evaluate this course. I had just an hour ago sent a reminder via iLearn, so you have a chance to evaluate this course. And I think we can be very fortunate. We had Rolf Hoyer here last week for a guest lecture, because I don't think there is any other quantum computing course in this world that had Rolf Hoyer as a guest lecturer. And now the second part of this course is your seminar presentations. And I'm sure you have lots of questions about this. And I would quickly, first of all, tell you what my expectations are. So we've now laid the foundations in this course. We've looked into lots of theory. And we saw the very foundation of quantum computers. And now your active role in this course is starting, where you start exploring one topic in greater detail. Could be an algorithm, could be a quantum architecture, could be some application or whatever. All of this is up to you. And what you're now expected to do is in January. So concretely, and you know the dates, in January, on January the 10th and January 11th, we will meet on campus for your seminar presentations. And you need to think now about a topic for your seminar presentation. Since most of you are from a technical discipline, most of you would be picking something technical, like an AI application, some quantum algorithm, some architecture, whatever. A few years ago, there was a mechanical engineering student. He wondered about challenges when it comes to manufacturing quantum computers. Something like this would be possible too. If you are from a more business related discipline, you could also pick a business related topic. But if you're studying for a technical degree program, you should also pick something technical. And your seminar presentation will be in groups of 2 to 3 students. It's really 2 to 3 students. It's not a single student and it's not 4 students. I received lots of questions about this by email and I rarely answered because 2 to 3, this is what I'm defining, not 1, not 4. You had to register for this examination in iLearn. I also received some emails 1 or 2 weeks ago. Some students struggle to sign up for this. Sorry, not iLearn, in Primus. And honestly, I don't know how to sign up for the examination in Primus. I don't have access to this, and I'm not an admin assistant. So for all the questions for signing up for an exam, so in Primus, please ask the admin assistants in the Center for Studies. But you need to sign up so that your mark appears in your transcript. And this was the schedule I talked about when we started with this course. I said we would finish the lecture sometime in early December. Now it's late November, so the original estimate was quite close. And you have to choose a topic now. In early December, you need to finalize your seminar topic. And for this, I also have a schedule that I will show you now. Um, when you open this iLearn course, as of 5 p.m. today, this submission portal will open and you need to submit not much, actually only a little bit. All you need to submit in there, and once the portal is open, you will see what you need to submit. You need to submit your presentation topic and your names and your student IDs. You don't need to upload any supplementary files. All I want to know at this stage is your seminar topic plus your names and student IDs. Then I had sent you various deadlines already a while back, and I updated this yesterday. You can, or you have to upload or submit your seminar topic plus your names and student IDs in the coming days. So the portal will open today at 5 p.m., or I will open it very quickly after the lecture, in fact. And the submission deadline is next week, Saturday. So Saturday, December the 6th at midnight. Then we will not have a lecture next week because next week you should still have some time to think about your seminar presentation. So we will only meet in 2 weeks again. And concretely, we will meet on December the 12th, which is in 2 weeks from now. And on that day, we will start with a guest lecture because we have a guest lecturer that's Dr. Patrick Mangard. He works for a federal agency in Germany for CITES, which is the Central Office for Information Technology in the security sector. And he will give a guest lecture, but we will probably not be able to record the guest lecture since he comes from national security. So please attend the live lecture. And after his guest lecture, which will take maybe 60 or 90 minutes, I don't know. So we will finish with the guest lecture around 3 or 3:30 p.m. After that, the floor is yours. And you briefly need to present your proposal. So you're picking now a seminar topic and you will do a proposal presentation. So you don't present your seminar presentation, but your proposal. And your proposal would take 1 or 2 minutes. You would just tell us what you want to do and maybe a brief structure of what your seminar presentation would be about. Can be something based on a paper, can be based also on an experiment. So if you want to implement code and you want to present us this, it's all fine. Can be experimental, can be based on literature. And your proposal presentation would just tell us what you want to do, in fact, and you would have 1 or 2 slides, not more. Because 140 students, or I think 144 students signed up for the examination. Now, if we say there are 2 to 3 students per group, we will have something like 50 or 60 groups. That means you should really stay in time, 1 to 2 minutes. Otherwise, we will finish very, very late in 2 weeks on Friday. I would give you feedback on your proposal. Maybe there are some other groups that want to explore the same topic. That's why you have to stay in that video. So, and this is also via Zoom. So you will stay in this video call until we finish on that Friday. And we may need longer than 10 past 5 p.m., but you have to stay in that call because someone else may have picked a very similar topic as yours. So you should be able to connect with each other and make sure that your presentations somehow differ or you're able to delimitate them. And the order in which you will do your proposal presentation is based on a list that I will put in Nextcloud. Because you will submit your topics until next week, Saturday. I will go through your submissions, create a list, and put it in Nextcloud. And just in the order of that list, you will give the proposal presentation. That's the easiest. I will give you feedback on your proposal. So if you present for 1 or 2 minutes, I'll give you feedback for 1 minute. And if it's 50 or 60 groups, we will probably finish a little bit after 10 past 5. Don't do your proposal for 5 to 10 minutes because we'll just run out of time. Then that's December the 12th. The following week is December the 19th. We will not have class because we have finished the lecture now. So you will have enough time to prepare your seminar presentation. Then we have the Christmas break. And after the Christmas break is Friday, January the 9th. We are not meeting for that because just on the following day, we start with the seminar presentations, which are on January 10 and 11. And there are a few more rules, and I've seen there are some questions in the chat. I'll get back to them in a few minutes. So this is the schedule. If you have any questions while you're preparing your seminar presentation, we can schedule a video call or meet on campus, but you would just send me an email and we schedule a meeting. So next week we will not have class. In 2 weeks we have the guest lecture and then the proposal presentations. In 3 weeks we don't have class, but we can schedule a meeting either on site or via Zoom if you have any questions. Then on December the 10th, you will give your seminar presentation and on January the 10th and January the 11th. And these seminar presentations, they will take place only on campus. And there are no special arrangements, whatever. We only offer them on campus. And your seminar presentation, so it's 2 or 3 students per group, your total presentation in January should take around 15 minutes. And there will be a 5-minute Q&A session after your presentation. Your presentation will be marked by me and by Professor Kuhnhardt. So Professor Kuhnhardt is my colleague who kept teaching this course together with me until last year, but he just retired. But he's coming back for that weekend for the marking. And you can score in your presentation up to 50 points. Up to 5 points for the motivation. So in the very beginning of your presentation, you would just say why you have picked that topic, why it's interesting, why it's useful. Any preliminaries that we may need. So if you talk, for example, about some encryption algorithm, assume that most in the audience are not experts in encryption. So provide us with the necessary preliminaries. Then do your actual content of the presentation. Your slides don't need to be professionally formatted, but if it's just a lot of plaque text on a white background and no figures, that does not look very nice. So you can score up to 5 points for the visualization. And after your 15-minute presentation, we'll do a 5-minute Q&A session. And the Q&A may cover everything discussed in class. So not just your presentation. And you can score 50 points in total. And 50 points will be a 1.0. 49 points will be a 1.1. But a 1.1 is not a valid mark in Germany, so we round this to your advantage. It's a 1.0. 48 is a 1.2, still a 1.0. 47 is a 1.3, which is a valid mark, and so forth. So if you score, I don't know, 38 points, that's a 2.2, which we round, and it's a 2.0. And you need 20 points to pass. So that's the marking. And a few more rules. I mentioned this when this course started. You will present either on the 10th or the 11th. You cannot pick the date or time. And you need to attend all the presentations on the day of your presentation. So if you present on the 10th, you need to be present all day on the 10th. If you present on the 11th, you need to be present all day on the 11th. You need to be there punctually at 8. We are starting at 8. And if you come late, you won't be able to enter the classroom and you will fail the course. And we will do some checks in between that everyone returned from lunch and so forth. And if you leave early, even after your presentation, you will fail the course because you're supposed to be there for all the presentations on that day because the Q&A involves you and you're supposed to learn from the other presentations. And I don't want to hear any excuses like if you live in Munich or that grandma died, whatever, you're supposed to be present on that day and you're unable to pick whether it's the 10th or the 11th. I will simply group these presentations also based on topic. For example, if 10 groups want to present about post-quantum encryption, I would move some on the 10th, some on the 11th, for example. But we in the 10th and the 11th will be quite full. So we are starting at 8 a.m. Maybe we finish at 5 p.m., maybe later. We don't know. It also depends on the number of presentations. Maybe we only finish, I don't know, at 8 p.m. So you're supposed to block all day long. And Horst and I will also be there all day long. Anyway, so those are the rules. And uh, one question is here, seminar topic. Yes, that's just a seminar title. So just the title, just the topic, what you will present, is what you submit. So for example, some algorithm or some architecture, and then your names and your student IDs. And these proposal presentations, they are online. So what we do in 2 weeks, it's all online because we have Patrick Mangat's guest lecture online and the proposal presentations will be online. We will only do the actual seminar presentations in January on site. Now, the next question is post-quantum encryption also a valid topic like lattice-based? Um, yeah, you can, but you would also then, so if you pick a post-quantum cryptography method, so one that cannot be broken efficiently by a quantum computer, you would you can present this, but you would also have to tell us why a quantum computer would not be able to crack that one efficiently. And then we make the link also to quantum computing better. So, and bear in mind this table here. So obviously you should spend most of the time of your 15 minutes on the content, not like 8 minutes on the preliminaries. So the number of points you can score here is somewhat indicative also for the time that you're supposed to spend on this. Are there any other questions? Who of you has already decided on a seminar topic? Maybe thumbs up or thumbs down? Largely positive response, but also negative, and you still have a bit more than 1 week, obviously. But you should start thinking about your topic very, very quickly. After we finish here today, I will also open the submission portal and you can submit anytime already if you wish. And as usual, all the deadlines are final, so you're unable to submit late, and you need to attend that session in 2 weeks when we discuss all the proposals and so forth. And you need to stay for all the proposal presentations just in case someone else picked a very similar topic as yours. Um, any other questions? If I shall wait for you, maybe send me some reaction in here. If I don't see any reaction, it means there are no questions. And with there not being any questions, now the one is coming as usual. Um, One student is still looking for group members. For this, we have this forum in the iLearn course where you can form groups, and you really have to find a group. You cannot present alone, but you can discuss this on campus or via this chat, via the forum. And we have never had that issue in the past that someone just couldn't find a group. Eventually, you'll be able to find a group, and don't run out of time because the submission deadline is next week, Saturday. So, with there not being any questions, I hope you have enjoyed the lecture and got a lot of insights into the theory of quantum computing. Don't forget to evaluate my course, and I look forward to your proposals in 2 weeks and then the seminar in January to see some in-depth presentations, and you will be able to learn lots of new stuff about quantum computing as well. So enjoy your weekend. Take care. Bye bye.